Hello, we're going to do whiteboard problem 10.9. It is looking at a cube that's launched by pulling back a spring 12 centimeters and releasing it. The spring constant is 65 newtons per meter. What is the cube's launch speed after it leaves the spring? Okay, and it's frictionless, so we know the coefficient of friction is 0. We want to find the speed. Okay. Let's go to our camera here. Okay. All right, I've got a little weird shadow going there. Okay, so our picture, right, is that we have some x equals 0 length, right, and the spring is compressed back here. The block is on the spring. The spring is going to expand back out, so we'll make like an after picture here. And when it crosses through the equilibrium, it's going to have some velocity. Okay, and then we know the spring constant k. The initial velocity is 0, right? And we want to know what v final equals. Okay, so let's do an energy bar chart. And if I look at the energies involved, I have some of the energy compressed in the spring. So I'm going to start with some potential energy in the spring. And it's not moving initially, so our kinetic energy initially is just 0. And then afterwards, it says there's no friction, so we don't need to worry about anything else happening as the block's sliding. So at the end, the spring will have stretched out back to its original length. So my spring energy is going to be 0. Spring final is 0. And I'm going to have some kinetic energy that will be equal to the energy stored in the spring originally. Okay, so this becomes my conservation of energy equation. So I have the energy stored in the spring. That is 1/2 k delta x squared. And I have my kinetic energy final, 1/2 m v final squared. Okay, and those are going to be equal to each other. Okay, so my delta x is 12 centimeters or 0.12 meters. Okay, and we want to find v final, so let's do our algebra first. But this seems really small, that looks better. Okay, so we can multiply both sides by 2, and then we divide by mass. So on the left, the 2 and the 1/2 go away, so I have k delta x squared over the mass. And on the right, I'm left with v final squared. So now I can take the square root of both sides, and let's just switch my order, and I get v final is the square root of k over m times delta x. And let's plug in our numbers now. So square root of k is 65 newtons per meter. My mass, what is my mass? Seems like I forgot to record that. 100 grams is my mass. So that's 0.1 kilograms. Thank you very much. I'll put that back in my givens there. Okay, so K is 65, M is 0.1 kilograms, and my delta X is 0.12 meters. And let's bring up our little Python window here. So I'm going to do the square root of, let's do square root of 65 divided by 0.1, and then times 0.12. So I get my final velocity is 3.06 meters per second. And let's just check and make sure those units work out right. So under the square root, I have a Newton divided by a meter divided by a kilogram. My Newton is a kilogram meter per second squared, and then I'm going to divide by a meter and divide by a kilogram. So those go away, that goes away. So I have, under the square root, I'm left with 1 over seconds squared, so that becomes 1 over seconds. And then outside the square root, I had a meter. So I multiply by a meter, and I get my meters per second. So that all checks out. Let's box our answer. And then again, look at all the elements that we have here for a good presentation, right? We have our given, we have the find, we have a diagram that shows what's happening in the kind of before and after in the problem. We have energy bar charts that are showing the energy initially and the energy at the end. Those translate into a conservation of energy equation. I've done my algebra first to solve for my unknown, the final. And I do that. I also check my units, and that all works out nicely. So those are all the elements that you want for full presentation points.